Okay, now we start the last session for today, for the second day of our conference. And the first speaker of this last session of the second day is our guest from Hungary, Daniel Gerbner, who will speak about generalized forbidden subposet problems.
Thank you. So this is joint work with Balázs Kiszeg and Balázs Patfos. So let me start with some notation. So I'm going to talk about families on a finite set, which I identify with the set of the first n integers and denote it with this square bracket. Our set is 2 to the n, so I'm going to talk about subfamilies of this one, and I'll often mention this particular family of all k element sets, which I denote this way, so it's a set, choose a number, and that's a family. Okay, so I'm going to talk about classes of sets of families or just properties of families, like and I'm first, so this is the introductory part. So the forbidden subposet problems without generalizations deal with the maximum cardinality of a set of a family satisfying some property. For example, family is an anti-chain if there are no two members which would contain each other. Okay. And so the full level that I mentioned is an obvious example for that, and the first theorem of this area is due to Gerbner, and it says that the maximal size, so the largest Gerbner families are indeed the largest levels. Okay? And so there are some more general inequalities. So we say that the family is k-Gerbner if there are no k plus 1 distinct members containing each other. And the example is that we can take at most k full levels, and the theorem of Gerbner says that this gives the maximum. Okay, so after and similar, more general inequality holds. So after that, the next question is, what if we define families by some other similar properties where we forbid some containment? So for example, the V is just 3 sets in this particular containment, so I hope the picture is clear that A is at the bottom of B and B and C are at the top, so the line between them represents containment, so that's why it's called V. And Katona and Tarjan considered them, and they proved that this is asymptotically given by the largest full level. Of course, if we take one full level, then we cannot have a V in that, and that's asymptotically the truth. So even more generally, we can take an arbitrary poset, so and we can consider if families. So the forbidden configuration is anything that can be defined using containment relations. And then the question is how large it can be. So the obvious idea is again to take some full levels, a family of full levels. So EP is the number that we can take EP many full consecutive levels. So in particular we can take EP the EP middle levels, the EP largest levels, without getting the copy of the poset. And the big conjecture of this area is that this is indeed asymptotically the optimal one. Okay, so our generalization is that instead of counting the number of sets in the family, we count the number of copies of another poset Q. So we are given two posets, P and Q, we forbid one, and we want to know how many copies of the other we can find in the family. So the other question for graphs has been studied, so there are several sporadic results, and a recent paper of Alon and Shikaman introduced this as a new area, but I'm not going to talk about this one. So here is our notation. So we forbid the first poset and count the copies of the second one. And in fact, we found the paper by Jussi Katona that dealt with these kind of things. So he, sorry, it's in a two-spanner family. So he forbid, so that's a mistake. So if you forbid chains of length 3 and count the maximum number of two chains, so that was studied by Katona, and nothing else before us. In fact, so two of the authors have already studied this for chains. So we forbid a long chain of length L and count the number of copies so we denote by pk the chain. So we count the number of copies of the shorter chain, and then we prove that the maximum is again if we consider an obviously PR3 family that consists of L minus 1 levels, that gives the maximum. Okay. So let CQF be the number of copies of Q in the family F. So our conjecture is similar to the big conjecture in the without the generalization, so that we can take a P3 family that consists of full levels, and that's asymptotically the best if we count, instead of the number of sets, if we count the number of copies of any Q. However, that of course doesn't have to be the family that consists of the middle levels, so they can be anywhere. Okay? So our first simple theorem is that if we forbid the V and we count P2, so the chain of length 2 consisting of two elements, so half of the V, then we can have at most n choose n half many copies. Okay? So an important thing is, an important observation is that if a family doesn't contain pk, then we can partition it into k minus 1 anti-chains. So we take the minimal elements, so those that do not contain any other set. That's obviously an anti-chain because it cannot contain a set that would contain another one. Okay, so and then we take another one. So for the remaining family, we take again the minimal ones. So the elements of F2 can contain the elements of F1, but nothing else, and so on and so on. And then we have to stop at k minus 1, otherwise you would also get a chain of length k. Okay, so how to use this canonical partition? So if we are given a V3 family F, then it is also P33. Probably I should have started with that one. So these are not induced subposet. So V just means that there is an A that's contained by two other sets. So if we have a chain of length 3, then the two larger members of that chain would contain the smallest one, so that would also be a copy of V. Okay? So it is P33, so we can into two empty chains. F1 is the smaller ones, F2 are the larger ones. So a member of F1 is contained in at most one other set in F, because with two sets it would make a V. So it is contained in at most one copy of V2, because it cannot contain a set and it's contained by one set. So obviously the number of copies of P2 is at most the number of sets in F1, which is an empty chain, so by Spenner's theorem we know that it's at most n to n half. On the other hand, we can take the family that consists of the middle level and additionally the full set. So one additional member of the family, that's the full set. And then we do know that indeed, so every member of the middle level is in a P2 together with the full set. Okay, so that was easy. Now here are some other posets we will consider. So the first one is N for obvious reason, the second one is the butterfly poset, so it's denoted by V. And then I already talked about V, so we can have, instead of two large sets, we can have R. So that picture. And DR is the diamond. Yes, okay. So I can see. So the next theorem is that if we forbid the butterfly and count the copies of diamond with R, I don't know what, so R middle sets, then the largest number can be n half choose R. So that many copies can we find at most. And well, so the proof is very similar, but okay, so I'm telling you quickly. So it's if it's B3, then it's also T43. Similarly, so we can partition it into three empty chains, and this time a member of the middle empty chain has this property that it is contained in at most one other set in F and contains at most one other set in F. So otherwise we will get a picture that looks like a Y, and that's also a copy of V if you think about it carefully. So and then it goes similarly that we have F2, sorry. So this has at most, so the size of F2 is at most n choose n half as well. And every copy of the diamond contains R sets from F2, so that is the upper bound. And the lower bound is given by the middle level together with two other sets, the full set and the empty set. Okay, so these are the easy ones I wanted to tell, and here is something a little bit more difficult. So we forbid P3 and we count VR. Okay. So the start is very similar. We consider F1 and F2, So if we have a copy of this VR, then it contains exactly one element from F1 and R element from F2 that contains it. Okay. So the larger sets Fi, they are from F2, so they form an antichain that contains F. So they all contain F and some other elements among the other m minus F elements that are not in F. So the best is if we take the largest antichain there, n minus F, choose n minus F over 2 any set. So these are the possibilities for Fi when we are given an F. So we have to choose R of them to count the number of copies of VR that contain F as the bottom vertex. So we have to sum it up for every F. So what we need to do after that is that we are given a Gerbner family F1, and instead of counting the number of its elements, we are given a weight function on every element that depends only on the weight, on the size of the set F. And it is in fact known that it is maximized if F1 is a full level. So after that we can see that the best is if F2 is also a full level, and then we just have to figure out for which level I we get the maximum, and then that also gives the lower bound. The family that where we pick I element and I half element sets. Okay, so I don't want to be too precise about it, and okay, so I just want to mention, so I mentioned that it is known what to do when the weight of a set depends only on the size of the set. So that's a very different topic that I want to briefly introduce, the profile vectors. Their study was started by Peter Erdős, Franke and Katona. So the profile vector of a family is an m plus 1 dimensional vector where the coordinates correspond to the possible set sizes, and I mean, so they are the number of the sets in F of that size. Okay. So if the weight depends only on the on the sizes of the sets, and the weight of a family is the sum of the weights, then the weight depends only on the profile vector. So instead of the families, we can talk about the profile vector. So this is how the weight of the family is equal to the weight of the profile vector if we define it that way. So now we are given a weight function and a set of vectors, and we have to find which vector has the largest weight. So in fact this weight function is also a vector, so this is just a scalar product, and then we know that that we are given a finite set of points and a finite set of vectors, then we can take the x-ring points, and no matter what the weight is, it is going to be maximized at an x-ring point. Okay. And then the theorem that we use about the Gerbner family says that these extreme points are indeed those families that correspond to full levels, plus the empty family, just to deal with the negative weights. Okay, so let's go back to our topic. So if we forbid P3 and we count the copies of n, then we don't have such a nice extra. So we know that it's at most little 2 to the 3n, and we have a lower bound that I'm not gonna talk too much about. So let me just sketch the proof of the upper bound. So similarly, we take the canonical partition, and then the copy of n contains two sets from the bottom part and two sets from the top part. So let me denote of n with these four letters. So B and C are the ones that have degree 2 in the picture of n. So we will count the copies of n according to them. So if we have a copy, an image of n, then we fix B and C. So for any particular B and C that are in a two chain in F, so that are in containment, C contains B, then we can pick D in a certain number of times, and we can pick B. We can pick A a certain number of times. More precisely, so the way to pick D is well, they contain B, which here I denote by F1. So they contain F1. So similarly to an earlier proof, we have n-1 choose n-1 half many ways to pick D after we fixed B and C, and F2 choose F2 half many ways to pick A after we fixed B and C to be F1 and F2. So this sum is an upper bound, and well, so that's about the first inequality. And for the second inequality, we use a more general version of profile vectors. So here we are given a two chain consisting of F1 and F2, and the weight on them that depends only on the size of the members of the two chain. And we know that that it is maximized on two full levels. So that gives the second inequality, and well, after this we can play a little bit with the binomial coefficients to get that this is at most little 2 to the 3n, and for the lower bound we just take two full levels and just optimize them. Okay, so let me go to a slightly different thing. So this was our main conjecture, that for any pair of posets, the maximum asymptotically is given by the union of full levels. So we say that this conjecture strongly holds if it's not only asymptotically, but it's strict equality. And we say that it almost holds if, well, so this of course, is much weaker than the conjecture itself. So instead of multiplying instead of checking the number of copies of Q in F and multiplying by something that is very close to 1, instead we multiply it with a polynomial, which can be of course very far from 1, but since it is exponential anyway, normally we can we can forget about the polynomial factor or say that it is negligible or whatever we want to say. Okay, so with these ones, so what we studied, and so these are the complete multi-level posets. So we have S levels, they are any size, and they are everything from level is containing everything from the levels above. So I hope that's obvious. So what we mostly studied is that we forbid a chain of length S plus 1, and we count copies of a complete S level poset. So only when it's one less, and then we can use the canonical partitions nicely. Okay. So we claim that in this case the conjecture almost holds, and additionally, if most of the levels have cardinality 1, so like in this picture, almost, so in the middle almost all have cardinality 1. So what we ask here is just that we don't have two levels next to each other that both would be larger than 1. So in this case the conjecture only holds. We know the exact number of, we don't know the exact number of the copies because we don't know which full levels we need to pick, but besides that we know. And in fact what we prove that these are more general theorems about processes that we glue together, and if you know something about the processes themselves, then we can say the same about the processes. The same about the processes when we glue them together, but I won't go into details. I just mentioned that we need to introduce and use new types of profile vectors, and that's all I wanted to say.
Thank you.